My name is Alan Stein. I work for InterDigital Communications, and John asked me to give you sort of an overview of VVC, what's new about it, why do we need a standard after HEVC, which was such a good codec, and so I'll just sort of give you sort of a foundation that will maybe help when the other speakers talk later in the day. Okay, so I'll give you a little bit an overview, talk a little bit about the new tools. I know there are a lot of non-engineers in the room, and you may glaze on some of that. Just raise your hand if it's painful. I'll give you a little bit of performance numbers. There are some. There's an article every week about VVC and other codecs performance numbers. I'll give you my take on that. Talk a little bit about deployment status and commercialization. I would note that we are 3 years after the what's called the FDIS spec, so 3 years after MPEG finished its work and sent the standard to ISO for the ISO blessing. 3 years is sort of a magic time in MPEG codec land. That's when we start to see product, and you'll hear about some of that. And then I'll talk about VVC and streaming in general, since we're at a streaming conference. Okay. So what is VVC? Just level set here. VVC is a next generation, very traditional video codec. So when I put up the architecture slide and you guys all freak out, this is what video codecs look like. They have these blocks, and the blocks do the things, and VVC is an evolution, not a revolution in video codec. Its performance gains come from a large number of improved tools. So in every little block in the diagram, there's been improvement. And so we see 35–40% over HEVC. And sorry, eyes are not what they used to be. And VVC also has added a few new tools that weren't in HEVC or previous codecs, and I'll talk a little bit about that, and I'm sure Tim will talk more about that, about RPR and the like. We'll get into that a little bit later. VVC's goals weren't quite as linear as H.264 and HEVC. H.264 was supposed to do HD. HEVC was supposed to do 4K. VVC is supposed to do lots of 4K better, 8K, 360, HDR, screen coding, a bunch of things. And that's why it was named Versatile Video Codec. It does a lot of things. There are a lot of use cases that drove VVC's design. Okay, so just to sort of, again, a little bit of a level set, what's a video codec? I don't have a laser pointer, but I guess I got to walk around with this thing. So for those in the room that don't know, what is standardized in MPEG is the decoder of video codec. The encoder is actually left for implementers to differentiate themselves. They actually don't tell you how to make a stream of bits that can produce a picture, but they say once you have these bits, you can reconstruct that picture on the right. So what's happened historically? Historically, going back to H.264. H.264 was finished in 2003. So this goes back to the end of the 90s when there was work where teams from ISO IEC, from the MPEG, MPEG is a part of ISO IEC, and from VCAG, Video Coding Experts Group, which is part of ITUT. These two standards organizations came together and they had joint teams. And so from 97 to 2003, the work was, the organization was called the Joint Video Team, JVT, and it produced the H.264 or MPEG AVC standard. And they have two names because they're two standards bodies. Then from 2005 to 13, they worked on HEVC, which is also known as H.265. And then from 2015 to 2020 or so, they worked on VVC, which is also called H.266. So, and again, the use cases are at the bottom. HD we got to HD with 264, we got to 4K and HDR with HEVC, but HDR wasn't completely fleshed out. And then we got to UHD, 4K and 8K, HDR, 360, screen content, and all these other things with VVC. So here's a good chart to sort of give you an understanding of how far we've come, right? I've said to people, if we had the pandemic in 2010 instead of 2020, we wouldn't be doing Zoom, right? We didn't have the compression ability, we didn't have the networks, and we wouldn't be doing video. We would have been screwed, basically. But here's sort of an interesting chart, right? So the chart on the left has sort of this long history going back to MPEG-2, and it is the bit rate that is needed to do HD. So back in MPEG-2 days, when I first started working on some of this stuff, 16, 17 megabits for one channel of HD video with MPEG-2. And then H.264 kind of cut that in half and maybe got it down to 8, right? And then HEVC maybe got it to 4. And now VVC gets it to about 2.5. So if you think about, any place that you have constrained bandwidth, you now have, 5x maybe versus what you had with MPEG-2, right? And so you can sort of see it by year, and again, we didn't want to get into VVC versus other codecs, but VVC came out a little bit later, but it really has it is the best codec that has ever been. So, I'm going to run out of time. I'm going to fly through some of this stuff. Okay, so this is really an eye chart, and it's really hard to see. And I apologize for that. I don't have the source for it, but it illustrates something important, and I'll move off it quickly. In the back here, in these colored blocks, you have what is a traditional video codec. You have quantization and motion compensation and all the interprediction and loop filtering and all the things that 264 had and HEVC had. And then with these blocks with the red outline are all the new tools, all the improvements. And so remember I said, VVC is getting us 35, 40%, maybe more versus HEVC. All of those were MPEG contributions that got beat up and evaluated and got gains, and the gains didn't take away the gains from the other tools, right? Everything has to be additive in order to get this 30, 40, 50%. And so, the takeaway from that is lots of improved tools and a couple of new ones. There's a tool down here called RPR. And like I said, it's called reference picture resizing. It's important. We'll talk about it a little bit later. Okay, same idea. Sort of a bunch of components of video codec and all the new stuff. So here's one of the more important tools, and I'm just going to blip through this illustration. In the old days, we had what were called macro blocks. We divided a picture into little blocks of 16 by 16 pixels. Everybody knows what a pixel is. These days, a macro block is actually 128 by 128, and it can be further subdivided. And I'll show you why that's important in a second. And it was 64 by 64 in HEVC, and it's more flexible now. So you basically say, well, if it's a background, I just want to do the whole thing as efficiently as possible. But if there are edges or texture or somebody's face, details, I want to subdivide, and I want to do those things differently. And so I'll give you a picture. I'm going to just jump through this one too. Same idea. Here's a picture to sort of illustrate. So what you're seeing is an image that is used in MPEG testing extensively, and you're seeing overlaid in green sort of what the encoder decided to do in terms of how big or small a block it wanted to work with. And so this is much more sophisticated in VVC than it was in previous codecs, and what you see is where there are lots of little blocks, there's lots of fine-grained detail. And those are coded more efficiently and more carefully than the big background blocks, right? These huge, big rectangles. Those can be, very easily coded with very few bits. And so you put the bits where the details are, and that's why it's better. Okay. Another tool, and again, for non-engineers, glazing. The takeaway here is intra-prediction is basically, I want this part of the picture looks like this part of the picture, and I'm going to steal those pixels and I'm going to copy them and kind of make a picture from another part of the picture. And the direction is, where can I go steal those pixels from? What we're seeing in black is what HEVC did, and what you see with the red and the blue is VVC has more ways to do that, a lot more ways to do that. That makes it actually hard for encoder vendors, but it's actually improving the picture quality at relatively low decoder cost. And I guess maybe it's a good time to say now, one of the more important attributes of VVC is improved compression efficiency without making the decoder much more complicated, because decoders go in consumer electronic devices, huge price sensitivities, and we kind of want to ride Moore's law, or better. And so, foreshadowing a little bit later on, I'll tell you what the result of that is. The other thing that happened during VVC standardization is there are additional things that aren't strictly required in VVC, but are important, and this is true for AVC and HEVC as well. And so things like dynamic metadata, like Dolby Vision or Advanced HDR by Technicolor, we have a way to put some of that information into a bit stream, and those are called SEI messages. Sorry, it's maybe a little deeply technical. All the SEI messages that came from H.264 and came from HEVC, they were all in the standards with those things. MPEG, JVIP pulled them all out, put them in its own standard that's called VSEI. So VSEI has a whole bunch of things, post-processing tools, new tools like film grain synthesis, which is, film grain is an interesting attribute of video. When you're looking at old films and you see that grainy pattern, Hollywood guys want that. They want that preserved. They do not want the encoders to take that away. But it's really, really expensive. It's a lot of bits to make that accurate. So there's actually a method where you can sort of say, okay, I see some film grain over here. I'm going to model it with parameters. I'm going to send it in one of these little SEI packets. And then at the decoder side, I'm going to bring it back. And so new tools like that are actually added into this VSEI standard, which accompanies VVC. Okay, told you I talk a little about performance. This is sort of a history chart, and I think it's a helpful illustration of what happens inside MPEG. When MPEG started on VVC, they had a few tools, they got 10% gains, they were happy. And then over time, more and more technologies were added, and it's not linear, but the gains started hitting 40%. But remember I said that the important figure of merit is decoder performance compared to previous generation. So this x-axis is actually the decoding time of VVC compared to decoding HEVC for the same video. So we want this less than 2x. 200% would be VVC is twice as complicated to decode as HEVC. And it actually turned out, over time, they got to around 1.6x. So if you think about it, 7 years later, Moore's law says you have a lot more compute power, but the decoder is only 1.6x as complex, and yet you've got 40% gains. That's actually a pretty good result. Same information in different form. These charts are really for MPEG engineers. They're called bitrate distortion curves, and the idea is up and left is good. Basically, you do a bunch of encodes, and you see how many bits it took and what the quality is. And there's a lot of debate about quality of PSNR and VMAF and a bunch of other metrics to say how is quality measured. This is it. The blue line's HEVC, the red line's VVC. So higher quality, fewer bits. Up and left is good. So what we see in these charts and subsequent charts is And these are hard pieces of content to encode. They're actually really challenging. So VVC is always up and left, significantly so, from HEVC. And the story gets better with some of the new tools. So this is actually a chart of the RPR tool. RPR stands for Reference Picture Resizing. Reference Picture Resizing means inside the video codec, all the pictures that it stores for some of its processing don't have to be stored just at one resolution. They can actually be used at multiple resolutions. It turns out that can give some gains. That can actually help. One day, TVs will be able to take a stream that has some 4K, some HD, maybe some 720, and upsample and display all of them, and that will be huge gains. But until that time, the RPR tool is actually, is ready for that consumer electronics evolution, but it still gives gains even when you do all the pictures the same size at the output. So again, up and left is good. The green in this case is HEVC, the light blue is VVC, and the dark blue is VVC with this new tool added. So you can see, not amazing gains, but still more gains. And again, VVC has headroom to get even better, and I think we'll hear from encoder vendors a little bit about that. Talk a little bit about deployment status. How am I doing on time? Okay, I still got a little bit. So after MPEG completes its work, VVC is brought to application standards. Application standards include organizations like ATSC, which does broadcast television in the US, SCTE, which does cable television in the US, DVB, which does broadcast cable, satellite, and streaming in Europe. SBTVD is actually the television standard in Brazil. -IF does standards for streaming, for MPEG-dash streaming. CTA Wave is an organization, CTA is the organization that puts on CES, but they also have a standardization division. And they're doing a project called CTA Wave, which is really an aggregation of streaming, and you'll start to see, I think this year, CTA Wave televisions and CTA Wave being an important standard in streaming. So VVC has either been adopted or is in the process of being adopted by all the standards noted on the left. Arrive is an Asian television standard. They're still working on it. ATSC is still working on it, but they've made public announcements. CTA Wave has added VVC into their standards. -IF has added VVC into its standards. DVB has added VVC. SBTVD, actually, this is interesting. There's a new television standard in Brazil called TV 3.0, and SBTVD is the organization that standardizes that. 140 million people. VVC is the codec for that new system, the one codec. And SCTE has adopted VVC for US cable. Commercially, people say, are there products? And I think you'll hear from some companies here today who have products for VVC. But what's interesting is there are a lot of software decode products. There are companies like Alibaba in China and Quai and companies that you're not hearing of, Tencent. They have VVC product. There are open source VVC software tools, including ways to make VVC work on web browsers. Now, you may remember that there was this big problem with HEVC in the past, that even if you had a laptop or a phone that had HEVC in hardware in the device, it still couldn't play in Chrome. And the reason was the software in the middle between Chrome and the chip didn't support HEVC. Well, there's now a workaround, and it's called WebAssembly. And it actually turns out that that's a really important tool to be able to say, I can get some software, like VVC decoder software, into a web browser without needing Google to update that middleware, per se. So there are encoders, there are hardware decoders. MediaTek has VVC support for up and down the line. 8K120 decoders. I mean, people are making big bets on VVC. We are 3 years after FDIS. We are at that point of first products. We're seeing chipset support, we're seeing encoder support, we're seeing support LG TVs. Some LG TVs actually support VVC now. This is the year. This is the year to watch VVC's liftoff. And this is pretty much what happened with HEVC. HEVC was standardized. HEVC was standardized in 13, and in 2016, you started to see the liftoff. So I think we're on track. Okay. And so I talked about this a little bit, but what's different from HEVC for streaming? Why, HEVC for streaming is not a huge success yet. And streaming has this problem of when streaming first took off and everybody bought Rokus. We have 3 televisions in my house. My wife bought 4 Rokus. This is a true story. All those devices only did H.264. So what Madeline Nolan, the president of ATSC, calls the launch codec kind of locks you in. So for broadcast TV, the launch codec was MPEG-2. And so all your TVs did MPEG-2. They didn't all do H.264. It was very hard for the broadcast industry to move off MPEG-2 and onto a new codec because video decoders are done in hardware. And if your hardware doesn't have the new codec, the person providing the service is very reluctant to move off the old codec. And so streaming now has the problem that broadcast had. Streaming is stuck on 264, and they want to go to HEVC because they'll get huge gains, right? HEVC over VVC is 50%. VVC is another 40%. You're talking about 3.5x if you can make the jump. But you have this legacy device support problem. But as I've said, what's different with VVC is we have this software, and I got to thank and really call out Fraunhofer HHI for putting into the world open source software called VV Inc. and VVDEC. This software is high performance, it's portable, and it is ported to web browsers. And that WebAssembly support is going to overcome, I think, a barrier that we had with Chrome and HEVC for several years. The other thing we have is we have an organization called MCIF. MCIF is a group that you'll maybe talk about. In its early days, it was focused on IP, but these days it's really focused on advocacy of MPEG codecs, particularly for VVC. MPEG needs a marketing department, and I say that a little bit, tongue in cheek. I am the marketing chair of MCIF, but look for MCIF to provide information to the industry to help people who don't read MPEG contributions understand what VVC is, how to use it, where the commercial status is, and I'm done. So thank you very much.